Hello, good day everyone. My name is Shivan Ramdani and this is my co-worker Surika Ramrup. And today we will be discussing an approach we use to integrate an inertial navigation system with the ROS1 navigation stack. So just before we actually go into the approach we use, I just kind of want to take a step back and look at one of the default localization methods available in the ROS navigation stack. So AMCL, if any of you have run the actual Turtlebot simulations on a system, you might be familiar with it. So just a high-level view of how AMCL works. It takes in dead reckoning data and laser scan data and tries to match up the scans with static obstacles in the global map. So, and based on the drift and translation from the dead reckoning, it tries to estimate and produce a transform between the world reference frame and the odometric reference frame. So far, so good? All right, perfect. So now I just kind of want to discuss our use case for what we were building this approach for. So our use case is actually a big, hefty robot in an airfield. So taking that into consideration and kind of looking back at what AMCL does, it kind of seems that AMCL will not actually be suitable for what we were trying to do, mainly because airfields are not known to have static maps. If they do, I would recommend you do not let anyone land a plane there. No, sure. All right. Sorry about that. All right. So given that we have all this large sensors on the system, we kind of try to come up with a concept to take in the sensor data, pass it through our workflow, and finally generate the relevant reference streams and transform data that will actually allow us to just send goals in the global map to the ROS navigation stack. Okay. So since Surika is a more capable and smarter person than me, I will now actually pass it on to her to actually go through more of this technical piece. Thank you.
So as Shivan just said, we use INS data, which is GPS and IMU data from a PixHawk, so it's already fused data. And we obtain odometry data as well, and TF data mapping the robot to the odometry frame. And our INS to TF node is able to generate world to odometry TF messages or robot to world TF messages, and also generates the robot pose. It then passes the relevant information to MoveBase, which is able to do trajectory planning in both local and global frames to allow our robot to navigate. So if we have both INS and odometry data, the transform tree we have is from map to odom to robot. And looking at the diagram, we see that the robot base link is placed in the local odometry frame, and the odometry frame is placed in the global map frame. Now, the origin of the map is entered by the user as a parameter as GPS coordinates. If odometry data is not available, the transform tree simply maps to robots, and it just the node directly publishes the transform between the robots and the map. Now, this isn't always advisable if your GPS isn't very accurate, because you'll have a lot of error in your localization estimates. So the reason for this, the transform rationale we have, is to allow the user to set goals in the global frame and then allow the robot, MoveBase, to plan both global and local plans. We have a TF3 comparison here that shows how AMCL is used with Turtlebot, and then how the INS to TF node was used with our robot. So it just simply replaces that AMCL node and publishes transforms between map and odometry frames. Okay, so if we have no odometry, the robot pose information is actually used to generate velocity information, which is fed via odom to MoveBase. And this velocity is calculated based on change in pose over time, and we use the map frame as both local and global frames. I'll now hand it over to Shivan, who will conclude our presentation.
Thank you. All right. So just to kind of discuss the performance of the system. In simulation, we are actually able to reach goals 100% of the times effectively, given that we actually gave it valid goals. simulations were carried out in Gazebo 7.14, and due to the hardware being outside the scope of what we had to do for this project and various mechanical and issues, we haven't actually been able to test this on hardware as of yet, but we plan to actually carry out hardware implementation in the up and coming months and hopefully get good results from it. Right. So that kind of concludes our presentation today. Are there any questions? But actually, before we actually do the questions, I just want to run the product of the system in the background. Right. So any questions?
Okay.
Yeah, did you make any improvements on localization recovery in case you lose like GPS signal and the localization? Like if you lose GPS, your robot might get delocalized quite a bit and filter might not find it anymore. Did you like made some strategies on how to recover the robot in these cases?
Well, right now, all it does is if you lose GPS signal, there's like a warning message, but we didn't actually implement that as yet. But it is a future thing that we would like to implement. Yeah.
Is there a maximum circular error probability for the GPS that you guys use for this?
Sorry?
Circular error probability for the GPS. How much can the GPS deflect before this starts becoming unstable, if anything?
Since we weren't actually able to carry out any hardware implementations as yet, we kind of, in simulation, we haven't actually encountered that error. So I guess we don't have a right answer for that right now.
So thank you very much.